Hello everyone, I'm Armeen Zahra, an aspiring astronomer, and welcome to episode number 9 of Cosmic Conversations, a series where I have the privilege of speaking with scientists, researchers, engineers, and innovators who are expanding our understanding of the universe. Through these conversations, we explore the research career journeys and the ideas shaping the future of space science. Today, we have an extremely special guest, Miss Seval. Miss Seval, can you introduce yourself?
Yes, my name is Seval Tasdemir, and I am the astrophysicist. I'm doing my PhD, and at the same time, I am the observatory supervisor. And now I'm the second and half year of my PhD, and hopefully, um, in 2 years, I will hoping to finish my PhD.
Great. So, my first question was that astronomy is fundamentally an observational science. We cannot physically interact with most of the phenomena we studied. So, we reconstruct the universe from the signals that reach us. So, how do you think about the boundary between what the data actually tells us and the interpretation we build around it?
Oh, I think this is the one of the most important question in astronomy. The data itself is usually more limited than the story we want to tell from it. Um, what we observe is as just a signal. We are looking at the sky as an astronomer, and we are just taking the photos. All we have is the light, and as you may know, light carries the information. To get this information, we need to make some tricks. For example, we have some kind of detectors, as you may know, CCD detectors or spectrometers. We collected the light, and this light comes for this light turns into the signals, and then we need to make the signals some meaningful for us, and we turn these signals as a numbers. Then we are applying some math, statistics, and physics on it, and after that we are trying to get information. As I told you, we observe the light as a signal, but from all those measurements, we try to infer things like the ages, masses, chemical compositions, distances, or evolutionary histories of an astronomical object. So there is always a layer of interpretation between the observation and the physical conclusion. For me, the the important point is to be very explicit about that boundaries. We should distinguish between what is directly measured, what is statistically inferred, and what is our physical interpretations. For example, I just wanted to give you example of my own research areas. I study about the star clusters. I may measure the positions and motions of stars with the space telescope, which is called Gaia, for example. But saying that two groups of stars form together or are dynamically related requires additional analysis and assumptions. The data can support that interpretation, yes, but it does not simply tell us the story by itself. So um, I see scientific rigor as being aware of where the data ends and where our interpretation begins, and continuously testing whether that interpretation survives alternative explanations. I hope that is enough for that question.
Yes, that clearly explains it. So, my next question was that after progressing from your undergraduate studies through a master's and now a PhD in astronomy, what is a question about the universe that has become more interesting to you precisely because you now understand how difficult it is to answer?
Yes, one question that has become much more interesting to me. The question, when I was a little kid, I was dream all the time becoming a scientific researcher in the future, and whenever I look at the sky, I was asking myself, what all these stars just formed, what how they far away from us. I was have some kind of curiosity how the universe began. And now I'm doing my PhD. I'm a researcher. This question still here. I'm still think and curious about the universes, how the universe formed in the first step. Yes, in the cosmology we have some answers about this question, but the first thing that we are missing, all the thing we have is just light. Light carries information, but in the first moment there were no light in the universe, so there is no info, which means there is no information. Yes, which means that we will not exactly know how the universe in the first steps formed and what was in there in the first time. So this is the most important question that I am trying to give. I'm trying to find some answer, but you know that everybody knows that unfortunately we will not learn about it.
Yes, that is indeed a really tricky question that scientists are studying.
Yes,
Now,
yes.
yes, in astronomy, we also often work with like we have incomplete, noisy, or indirect data. So, at what point does a pattern in astronomical data become convincing enough to be considered a meaningful scientific result rather than simply that it's just an interesting possibility?
Just for me, a pattern becomes scientifically meaningful when it is not only visible in the data, but also statistically significant, physically plausible, and robust against reasonable alternative explanations. Yes, we can see any pattern in the usually the first step, not which is not the final result. For example, I can give you an example on my own research. For example, I'm working on stellar groups. If I find that two stellar groups have similar positions and proper motions, that is, yes, interesting. But I would then ask, is the similarity statistically significant, or could it happen by chance? This is another possibility. Do they also have consistent distance, ages, or chemical properties? And and does their dynamically history support the same interpretations? I I also think reproducibility is extremely important. If if a result changes dramatically depending on one particular selection criterion or one particular model, then I would be cautious about making a strong claim. So I would say that confidence comes from convergence of independent evidence. One piece of evidence can suggest a possibility, yeah, but several independent lines of evidence pointing toward the same conclusion can turn that possibility into a scientific result.
Thank you so much for this detailed answer. And my next question was that you work both as a researcher and as an observatory operations supervisor as well. So, has working on both sides changed the way you understand what it actually takes to turn an astronomical observation into reliable scientific evidence?
Oh, yeah, absolutely. Absolutely. I think working at an observatory has made me much more conscious of the fact that scientific data does not simply appear as a perfect data set. As researchers, yeah, we are using a beautiful organized catalog and start analyzing it. This part is so much fancy because you are not doing any observation and these data sets are just public. But behind that catalogs, there is an entire observational process, and this is another big area of the astronomy. And you need to take into account the weather conditions, atmospheric effects, seeing factor, instrument performance, calibrations, detector characteristics, observing strategy, data reduction, and many, many other factors. And working on the operational side has really helped me appreciate how every observation has a history. And it has also made me more cautious, as I told you, when interpreting the data, because if something looks unusual in your data set, you need to think about the data, because there were any biases, yeah, and you need to make some corrections on your data. So in that aspect, it's really helped me to think about um, these issues. So I think the two roles complement each other very well. So research teaches me how to extract scientific information from observation, while observatory work reminds me to respect the limitations and the uncertainties of those observations.
Right. And my next question was related to astronomical images. When we basically see astronomical images, it can make the universe look almost effortless to understand. But behind a single image, like you just explained, there can be calibration, atmospheric effects, instrument limitations, data processing, and interpretation, like a lot of things, just like you mentioned. So, what is one thing people generally don't realize they're looking at when they see a beautiful astronomical image?
Oh yeah, this is another fancy question. I think people often don't realize that an astronomical image is not a simply photograph in the ordinary sense. Because, for example, I love to take photos anywhere where I go, but the space objects are so much far away from us. For example, I can take a photos of a flower, it's so close to me, but if I want to take a photo of the Jupiter, the whole system is changing. What people see is usually the final result of the long, long chain of measurements and processing steps. The image may contain information collected over many exposures. There may have been corrections for the detector effects, atmospheric conditions, as you said, background light, calibration, and instrumental limitations. Sometimes different filters or wavelengths are combined to create the final image. And there is another important point, that the colors themselves may not always represent what our eyes would see, because our eyes also limited. Well, when people look at a beautiful image of nebula or galaxy, they're often looking at a scientific visualization of data, not simply a direct picture of an object. And I actually think that makes the image even more beautiful, yeah, because behind that image there is not only aesthetics, there is measurement, physics, technology, and huge amount of human effort. But unfortunately, people don't know the background of these images. They just only have some disappointments about what they see. For example, um, some people comes to see Jupiter or Saturn, they are imagining, they are thinking that yes, we will see the Saturn as the photos NASA's published, but when they see exactly the Jupiter or Saturn, they are just they are just looking sad, because they said that we don't expect to see something like that. It's just a dot. It's, for example, they are looking at the Mars and they are saying it's just a little red dot, but um, we are so far away from each other, and the it is important. It is impossible to see Mars as the pictures NASA shared. So yeah, this is it.
Right, like all of the things that you just said, I completely agree with those. So, my next question was that as astronomy enters an era of enormous astronomical surveys and increasingly powerful AI tools, So, do you think the greatest challenge for the next generation will be obtaining better data or knowing which questions are actually worth asking of all that data?
Yeah, that's a good question. I think increasingly the challenge will be knowing which questions are worth asking. Yes, I all the time recommend my students, my colleagues to use artificial intelligence. It is help us to save time, but um, it will brings some problem altogether. We are entering an extraordinary period in astronomy. Surveys are producing enormous amounts of data, and AI and machine learning techniques allow us to process information at a scale that would have been impossible before. But having more data does not automatically mean having more understanding. In fact, I think there is a danger of becoming very good at finding patterns without necessarily understanding what those patterns mean physically. So I see AI as a very powerful tool, but not as a replacement for scientific curiosity and critical thinking. The important question is not only what can we find in this data set, but also why does this matter and what physical questions are we trying to answer. For the next generation of astronomers, I think the ability to formulate meaningful questions will become just as important as the ability to analyze large data sets, because the scientific problems is much more important than the um, analyzes processes.
Absolutely. My next question was that as an astronomy instructor, you aren't only teaching students facts about stars and galaxies, you're also introducing them to a way of thinking about evidence and uncertainty. So, what is one misconception about science that you wish you could correct in every student who enters your classroom?
Yes, definitely. I have the thing that I want to change my students' mind. One misconception I would really like to correct is the idea that science is a collection of facts that scientists already know to be true. Scientists, science is actually much more about asking questions, testing ideas, and dealing with uncertainty. Students sometimes think that if scientists disagree or if a result has an uncertainty, then science is somehow weak. Um, I'm trying to explain the opposite. Uncertainty is not a failure of science. Quantifying uncertainty is one of the things that makes science reliable, because we unfortunately can't say that this is 100% is true or this is 100% is false. That we are just talking about all the time possibilities. I also want students to understand that changing your mind when new evidence appears is not a weakness. It is actually one of the strengths of scientific method. So if I could leave every student with one idea, it would be this: science is not about being certain all the time. It is about having good reasons for what you believe and being willing to change those beliefs when better evidence comes along.
Right. Now, the next question was related to light pollution. So, how does light pollution affect astronomical observations? And what do you think are its major sources? And also, what practical measures can like astronomers and communities around the world take to reduce its impact while also preserving the night sky?
Um, the light pollution is the most important problem in our area. Uh, I all the time love to see the sky, stars, but unfortunately, in the cities, there is a huge amount of light pollution. We have an observatory, but unfortunately, because of the light pollution, we can see the stars. Only thing that we see is just Jupiter, Saturn, Venus, and Moon, and some bright stars. And this is unfortunately so bad thing in that area, because there are lots of things that we can see because we have telescope. We can see nebulas, we can see galaxies, Andromeda, and any other things. But because of the light pollution, we can't see those of astronomical objects, and only thing that we see is, as I told you, very limited objects. Uh, can you repeat the last part of the questions?
Yes, sure. So the last part was that what practical measures can be taken by astronomers and communities so that we can reduce its impact?
Um, Unfortunately, in the small observatories, I think there is no practical solutions, but the bigger observatories using some any other techniques to um, to get rid of these problems. For example, adaptive optic techniques. But in the small observatories, unfortunately, I don't know. There is no practical solutions.
Right. Can you also like give an example from your real life when light pollution has affected you personally in your field of astronomy?
Yes, for example, a couple months ago, I was making an observation with my students, and only thing that I show my students is Venus and Jupiter and Galilean moons, and I couldn't show any other object of because there are so much light in the side of my observatory. We can see some star clusters, globular clusters, but because of the light pollution, we can't see.
Right. Now, my last question was that after spending years studying the universe scientifically, so has your relationship with the night sky changed? And do you experience it more analytically, more emotionally, or somehow both?
Oh yeah, definitely both. When I was a little kid, as I told you, I could look at the night sky, and I just simply think, yeah, this is beautiful, awesome. Now I'm still have the same enthusiasm inside me, and I'm looking at it. I often know more about what I'm seeing. I might recognize the constellations, think about the distance of a star, or wonder about its physical properties and evolutionary story. When I was a little kid, I had no idea what kind of evolutionary story. I didn't know stars can actually die or star can actually born. So now, since I know this physical background of this objects, I'm looking at the situation a little bit analytically. So in one sense, I can say that I've become more analytical. But strangely, knowing more has not made me sky less mysterious or less beautiful. I think it has made it much more meaningful. When you understand that a point of light may be a star hundreds or thousands of light years away, that is, light has been traveling toward us for centuries, and that we are reconstructing its history from that tiny little tiny signal, that the experience becomes even more extraordinary for me. So I would say that astronomy has changed the way I look at the night sky, but it has not replaced the sense of wonder. It has added another layer to it. I just can look at the sky as a scientist and ask what I am seeing, but I can also simply look up and think, how incredible is that we are here, able to see it and ask these questions. Yeah,
Thank you so much for like these amazing answers and having a conversation with me. I'm truly grateful that you took out your precious time and you basically gave this interview.
I'm really happy to hear that all nice words.